Hello, welcome back to ReddyControls. We are starting a new playlist, and this playlist is all about analog inputs and outputs in PLC. Whether you are a beginner technician or an engineer moving into advanced process controls, this playlist will help you. This playlist will have about 6 videos. In the first video, we'll understand about 0 to 10 volt and 4 to 20 milliamp signals, and followed with choosing the right compact logics analog IO modules. And then we'll talk about wire sensors, transmitters, and actuators. Then we'll configure some analog signals in Studio 5000, scale them, and then apply the analog control in real world applications like tank level. So without getting delayed, let's jump into the first video in this series, which is what are analog signals. What you learn in this first video is you'll understand what analog signals are and how they are different from digital signals, and we'll learn about different type of analog signals used in industrial automation. Why does it matter? Why do we need to learn about analog input output signals? Is analog input output enables the PLCs to interpret real world data like temperature, pressure, and level, which can't be interrupted by digital systems, right? The PLC or any computer systems only understands ones and zero, but in order to understand or interpret a continuous values or continuous signals, we need to have a analog interface cards which will help the PLCs. And some of the industrial applications are we'll explore the tank level monitoring, curing pressure sensors, and analog outputs to VFDs. Some of the signal standards we'll also talk about is discover the 4 to 20 milliamp loops, why they are standard, and how they provide noise immunity. So let's understand the fundamental differences, right? What is binary versus continuous? Binary or digital discrete signals. These are either signals which are on or off, like a push button, which is a when you close the contacts on the when you push the push button, the contacts on the back close, which is represented by a 1, and when it's open, it's 0, right? So that's a digital signal. It's either in 1 or a 0 state, either it's on or off state, either it's low or high state. When it comes to analog signals, on the other hand, they vary continuously and they can represent a range of values. Examples are digital signals. We talked about push buttons or a proc sensor. Examples of analog signals are thermocouples, RTDs, pressure sensors, and potentiometers. Signal processing. Discrete signals are directly read by the PLCs, whereas analog signals require conversions through a analog input modules or a analog to digital conversion modules. Some of the use case suitability is for a digital IO, it's for simple state detection, whereas for analog IO is for process monitoring, including flow, temperature, level, and other continuous variables. Why analog inputs are needed? PLCs are digital devices, as we spoke about. PLCs can operate using binary logic, which means they inherently cannot process analog signals without conversion. That's where the analog input modules come in, where they convert continuous analog signals like voltage or current into digital values so that the PLC can process and typically stores them in dedicated registers. This one, the image is showing is a flow transducer. It has a set point where you could teach, like if you see a flow of X units, make an input high. Whereas you also get sensor integration. Some field devices like thermocouples and load cells, they give you an analog value in terms of voltage or current that has to be read and interpreted accurately. Uh, Analog inputs and outputs are essential for complex controls, whereas such as batching, feedback loops, and variable motor control rely on analog input for precision and adaptability. Common analog input voltage ranges are, you could find unipolar voltage ranges that are from 0 to 1 and 0 to 5 or 0 to 10 VDC, commonly used in sensor output and analog controllers. Binary voltage ranges are plus or minus 5 degree and plus or minus 10 VDC ranges, used for signals that might fluctuate above and beyond 0, enabling symmetrical monitoring. 4 to 20 milliamp current loops are industry standard for analog signal transmissions. Provides resistance to electrical noises and detects signal loss below 4 milliamp. Choosing the right range depends on your device specs, distance and accuracy needed, and electrical environment. Current loops are preferred for long distance and EMI prone setups. Resolution and AD. So what is a resolution? For every analog to digital conversion, when they transform analog values into analog voltages or currents into digital numbers that a PLC can read and store, have something called as a resolution. The resolution is the smallest amount of change that can be detected by the ADC, determined by the number of bits. More bits is higher precision. Common resolutions are a 12-bit analog to digital conversion that produces 2 to the power of 12, that is 4096 discrete steps. Or you have 16-bit that yields about 65,536 steps. Higher resolution is ideal for fine control and measurement. Compact Logics offers a 12-bit resolution, whereas Control Logics analog cards give us 16-bit resolution. Mapping signals to count. Example, say you have a 0 to 10 volts coming from a um, sensor. If you map that into a 12-bit, you'll have 0 to 495 counts, right? So if you take the resolution, that's about each count is about 2.4 millivolt. So you take 0 to 10 and you divide it across 4095 steps. That gives you 2.44 millivolt as a resolution per count. Real world application of analog IOs, tank level monitoring. Analog sensors measure the fluid levels in the tanks using 4 to 20 milliamp signals, allowing precise inventory control and automation of refill processes. Temperature transmitters, RTDs and thermocouples output analog signals that are converted into temp readings for ovens and curing presses. Pressure in the curing press. Analog pressure transmitters ensure consistent pressure levels in industrial curing processes, critical for product quality. Analog output to VFDs, 0 to 10 volt signals from the PLC are used to control variable frequency drives, enabling precise motor control. So what do we choose? 0 to 12 volt or 4 to 20 milliamp signals? It depends on the application, but if you have a signal transmission distance of longer, then you use a 4 to 20 milliamp to reduce electrical noises. And if you want failure detection, current loops detects faults if signal drops below 4 millivolt. Voltage based systems lack this built-in diagnostic capability. Simplicity, if you want a simpler thing, use 0 to 10 volt is easier to implement in short range applications, but 4 to 20 milliamp offers greatest robustness in industrial environments. When it comes to accuracy, voltage signals can suffer from voltage drop. Current signals ensure consistent current flow across load, improving precision. Troubleshooting analog input output. If you're not receiving any signal, just check the fundamentals, which is ensure the sensor has power and ensure the correct range is selected and ensure PLC configuration. If you're seeing noisy readings, then it could be by grounding issue like a noise or shielded cables, especially in voltage based signals. Make sure it's grounded only on one side to avoid any loops. Incorrect scaling, mismatch between the input signal and PLC can result in a data overflow issue. Drift or offset, sometimes the component aging or temperature changes may cause drift. Regular calibration is needed for accuracy. So wrap up on the first video, analog IOs are essential. Industry standards do matter. We do have a 4 to 20 milliamp and 0 to 10 volt, and precision requires resolution. So higher bit AD converters offer more accuracy. Real world impact, analog IO powers the automation behind tank levels, motor speeds, and environmental monitoring, bringing digital control to physical processes. If you like this video, please share and subscribe and leave a comment. Until then, I will see you in the next video. Thank you.